All right, so we spent time on learning kind of like the general um, approach for the library of function. We look at different functions first at the beginning, and then we focus on individual functions like linear functions, quadratic functions, and then more general form of that is polynomial function, the power functions. We then switch to rational functions. Okay. Now, in order to do all the type of function, you need more theory or more background in order to do exponential functions, logarithmic functions, and later on trigonometry functions. All right. Even though that we need this type of theory in lecture 17, composite functions, but we have enough functions to do all the type of operations. So let's say you have let's say you have polynomial function and rational function. You can add them together. You can perform subtraction, you can perform multiplications and divisions on different types of functions. You can add one linear function with another power function, your choice. If you have a reciprocal function 1 over x, you can add, subtract, or multiply a quadratic function, for example. So that is the idea of something called combined functions, right? You have multiple functions, you can perform addition, subtraction, multiplication, and divisions. And then toward the end of lecture 17, there is another type of combined functions that is very helpful for us to understand in order to learn exponential function and logarithmic function. That is called composite function, compositions of functions. But for now, let me focus on combined function first. Combined function means that you have two function or multiple function and you do addition, subtraction, multiplications, and divisions. Okay. It's very simple. Just that this is you have a new type of notation that you may want to familiarize yourself with. So the first type of combined function is the sum function, and then the difference function, then product, and then quotient. So for the sum function, the notation is f plus g of x, given that you have two functions, f of x and g of x. Therefore, the sum of these two functions is written as f plus g of x, or more explicitly, that is f of x plus g of x. Unfortunately, because you combine different type of functions, the domain of the combined functions is not as straightforward as finding the domain of the individual functions. All right. So the domain of the function is going to be A intersect with B. All right, so this is new, but so far when you find the domain of the function, we use union notation. But when finding the domain of a combined function, we use the intersection notation. Okay? Given that A is the domain of F and B is the domain of G. We're not going to focus too much on finding the domain of a combined function because it gets quite complicated for different functions, especially when you get to a rational function. Get quite complicated, but that is the idea I want to mention that to you, that the domain of the combined function, in this case, the sum function, is the intersection between the two domains. Now for the difference, the notation is very similar to the sum. You just switch the plus side with the negative sign. So you have f minus g of x is equal to f of x minus g of x. And the domain also going to be A intersect with B. So for additions, when you do f plus g is going to be the same with g plus f. you're okay with that. However, you cannot say the same thing for the difference. So f minus g is different from g minus f. So g minus f of x is equal to g of x minus f of x. But the domains stay the same. There's still the intersection between the two domain A and B. Now for the product of two functions, you do f g of x is equal to f of x times g of x. The domain is still A intersect with B. And for quotient, the notation is f over g of x is equal to f of x over g of x. Now this is where it gets complicated. For this is a fractions. Okay. The domain is still A intersect with B. But you need one more condition that in this case, g of x has to be different from 0. All right, so that's the four combined functions that we want to look at in the first half of the lecture. The sum functions, the difference functions, product functions, and quotient function. All right, so let's do some exercise on combining functions. So if I have two functions in this case, f of x equal to 2x plus 1 and g of x is x squared minus 1. So these two are polynomial functions. They are nice functions, easy to find domain. Okay. So for f of x, this is a linear function or polynomial function of degree 1. And g of x is a quadratic function or polynomial function of degree 2. So therefore, the domain of f is whole numbers, infinity, and the domain of g is the same thing, All right, so a few notes I want to include here. So this is a linear function, or this is polynomial functions of degree 1. And g of x is the quadratic function. Or this is a polynomial function of degree 2. The domain of f is all real numbers. Or from negative infinity to positive infinity. And the domain of g is from negative infinity to positive infinity as well. All right, so now part A, we want to find the sum functions. So f plus g of x is equal to f of x plus g of x. So f of x is 2x plus 1. And then g of x is x squared minus 1. Then you combine these two functions together, you get x squared plus 2x. So the domain of this function is, again, all real numbers, infinity to positive infinity. Why? Because the domain of f is all real numbers, intersect with the domain of g, again, all real numbers. Therefore, the intersection should be real numbers. So the domain of the sum is all real numbers or from negative infinity to positive infinity. Now part B is the difference functions. So f minus g of x is equal to f of x minus g of x. So when you have a negative in place, be careful when you write the answer. So f of x is 2x plus 1 minus x squared minus 1. So the x squared minus 1, I put that in the parentheses because I have a negative sign in front of it. Now, if I want to expand this negative, I need to distribute negative into x squared and negative into negative 1. So this is what I get. 2x plus 1 minus x squared plus 1. So you have negative x squared plus 2x plus 2. And the domain of this function, again, is the intersection between the domain of f and the domain of g. So the domain of a difference is all real numbers or from negative infinity to positive infinity. Good. Now the next one is the product function. So you do f, then g, or you can write f times g. So f times g of x is f of x times g of x. So f of x is 2x plus 1 times x squared minus 1. Right, so that's the product functions. And the domain of the product, again, is all real numbers or from negative infinity to positive infinity. Next one is the quotient function. You have f over g of x is equal to f of x over g of x. Or you have 2x plus 1 divided by x squared minus 1. So that's the difference quotient, or difference function. So the domain is, again, the intersection between the domain of f and the domain of g. But for the quotient function, you need to include one more condition that it's 0. So in this case, the domain is everything except negative 1 and 4. So the domain of the quotient is all real number except negative 1 and 1. Or you can write from negative infinity to negative 1, union with negative 1 to positive infinity, union with positive 1 to positive infinity. Good. Any questions?
Firstly, why do you not foil?
That's a good question. To be honest, this is always good to just, what is the idea here? I want to do that. And given two functions, we can do addition, subtraction, divisions. Okay. So by doing this, you show that okay, you can multiply two functions together, and that is you don't have to necessarily foil that. So that's always good questions to look answer. It depends on the problem, it depends on the context that you want to foil it. So in this context, it's not necessary. But if you want, you can. All right. So before the exam, we start covering new topics called combined functions. Okay. We're going to build up some background on combined function before we get into composite function. Composite function is another way to combine two or more functions together. Before we get to composite function, we want to talk about combined functions. So combined functions, we can operate on different functions. We can do summations. We can add two functions together. We can subtract one another and multiply two functions together and find divide one function by another. And when you combine two functions, finding the domain of the function is a little bit more tricky. The domain of some difference, product, and quotients, they all have similarity that the domain is the intersection between the two domains. For capital A is the domain of F and capital B is the domain of G. But for quotient functions, you need to make recognitions that G of X has to be different from zero because G of X is the denominator function. We did one example that you have two polynomial functions here. One is a linear function and the other one is a direct function. We do additions, subtraction, and divisions. And we also find the domain of the combined functions. Right. And for the domain of the quotient functions, we exclude the value in the denominator. In this case, that is -1, 1. All right. So now let's try another example, example 2. So for example 2, you have two functions. One is a quadratic function x squared minus 1. And the second function p of x is 1 over x. This is the reciprocal functions. So here I want to point out that f of x is a polynomial function of degree 2. And g of x is a reciprocal function. All right, so as we learned before, the domain of polynomial function of any polynomial function is all real numbers. And the domain of the reciprocal in this case is the rational function, is that of everything except 0. Right. So the domain of f is all real numbers. And the domain of g is everything except the element 0. So that's the setup. Now we get to the combined functions. So the first one is the sum functions, f plus g of x. So this is
equal to f of x plus g of x. Right. So again, I want to mention this is the sum function. So for sum function, you just add the two functions together. So x squared minus 1 plus 1 over x. That is that simple, man. Now the domain of the sum, in this case, again, in finding the domain of the combined function, you find the intersections of the two domains. So in this case, the domain of f is all real numbers, the domain of g is all real numbers except 0. So if you find the intersection between these two domains, you're going to have the domain of the sum is all real numbers except 0. Or you can write from negative infinity to 0 union with 0 to positive infinity. And we're going to perform similar calculations on the difference functions. So f minus g of x is equal to f of x minus g of x. Again, this is the difference function. And you get f of x to be x squared minus 1 minus g of x, which is 1 over x. And the domain of the difference is all real numbers except 0 as well. And the question so far? Okay. Now the next one is the product function. So f times g of x is equal to f of x times g of x. So this is product function. You get f of x to be x squared minus 1 times g of x, which is 1 over x. So you can write it like this, or you combine this two together, and you have a different way to present this. You can write this as x squared over 1, sorry, x squared minus 1 over x. So this two, the same. And the domain of the product is again all real numbers except 0. Now the last one is the quotient functions. So f over g of x is f of x over g of x. It's the quotient function. Okay. So here's the setup. So f of x is again x squared minus 1 over x. Okay. So you, because you divide a fractions, can multiply by the reciprocal. So you have x squared minus 1 times x. So that's the answer. Find it. This is very convenient. Don't have to buy new stuff.
Okay, so as you can see, in finding the domain of quotient functions, you have the domain to be the intersection between capital A and capital B. And also you need to impose another condition that the denominator cannot be zero. So in this case, you need to run 1 over x to be different from 0. You with me on this? However, 1 over x is always different from 0, no matter what value of x you put. You with me on that? Good, good. Okay. So that's why you can't, in this particular case, you can just ignore this condition. Because 1 over x is always different from 0. Okay, good. So therefore,
The domain of the quotient is always all real numbers except 0.
so this to indicate that the domain is the intersection between capital A and capital B and a conditions, but we just ignore that condition. All right. Any questions, concerns, comments? Okay, I'm gonna move on to another topic. This is another way to combine two functions together. This is called compositions of functions, so function within function. Okay, so now let's given two functions, the compositions of functions.
Denoted as f.
Now be careful here.
Circle
Write a little circle there.
f circle g of x.
So you have to explicitly write down the circle, small circle, to indicate that is the composition of functions, or you want to compose two functions together.
Is defined as, so f circle with g of x is equal to f of g of x.
So this is called a composite function or composition of functions. So in composite function or composition of function, it really matter the way you write it, the order on which you write f and g. Very important.
So in this case, you say g of x is called the inside function. And f is called the outside function.
What the heck is this? Didn't even realize I wrote it. All right, so later on, we're gonna encounter a different way to combine or make a composition of two functions, okay? So as I mentioned, it's really matter the way you write f and g, the order on which you write f and g. So f circle with g of x will have a different answer to g circle with f of x. Okay, so in the first case, on the left-hand side, you have this to be f of g of x. All right, so g of x is the inside functions. Now on the right-hand side, you have g of f of x. Okay, so f of x is in this case the inside function. Okay,
And again, I mentioned that last time we need to learn how to do compositions of function or find composite functions, because eventually after this lecture, we're going to learn exponential function and logarithmic functions. And they are inverses of one another. Right? And in order to show that two functions are inverses of one another, you need to show the two conditions, or technically just one condition. This is called cancellation property. And when you have cancellations property, you need to perform compositions of functions. F of g of x will be equal to x for inverse functions. And g composed with f, or in this case, g of f of x, going to be equal to x as well. Okay. So again, in order to show that two functions are inverses of one another, in our example, exponential function and logarithmic function, we need to show that this should be equal and equal to x. And in order to show it, you need to know how to perform compositions of functions. Good. All right. So having said that, let's move on to example. So in this example, you are given two functions, x squared and x minus 1. So I want you to determine the following compositions of function. So f circle with g of x is equal to f of g of x. So in this case, g of x is a inside function. So you know g of x, you take out g of x and you replace by x minus 1 in this case. So you are calculating f of x minus 1. I thought this was genius idea. So we do the same thing for all of them. Now my bag is so organized. I was like so happy. I did that at 4 in the morning. So I wake up in the middle of and I was like, this is it. Finally, after like 40 years in school, finally figured this out. Anyway, so what are we calculating? So f of x minus 1. So you have f of x to be x squared. So x squared. You okay with this? What are we trying to do? We're trying to calculate f of x minus 1. So take this out, and replace that with x minus 1. You get the answer. You got it? Okay. So f of g of x on the composition of these two functions give you x minus 1 squared. So this give me x minus 1 squared. Now for g circle with f of x, you have this is g of f of x or g of, so f of x is equal to x squared. You remove f of x and you replace that with x squared. So g of x is equal to x minus 1. So what are we trying to do? We try to calculate g of x squared. So you take out the x and you replace by x squared. So the second composite function will give you x squared minus 1. Any questions? We good? Does that make sense to you? Okay. Now, f circle with itself or f of x. And f of x is equal to x squared. So what you technically want to do is calculating f of x squared. So f of x here is equal to x squared. Right. Again, what are we trying to do? We're trying to calculating f of x squared. Take out the x and replace that with x squared. You okay with this? All right, so technically this is what we have, x square, well, this is equal to x to the fourth power. Any questions on C? Now for D, you have G circle with itself. This gives you G of x. And G of x is equal to x minus 1. So you calculating G of x minus 1. And do this, G of x is equal to x minus 1. And we want to find G of x minus 1. So take out the x and replace that with x minus 1. And then you can combine or manipulate this, and you get x minus 2. So this give me x minus 1 is equal to x minus 2. Okay. Any questions on example 3? Now let's do example 4. I'm going to perform the calculations for part A only. I'm going to turn that to you to perform part B, C, and D and see what we got. Okay. So for A, f composes with g of x, or this is equal to f of g of x. In this case, g of x is equal to 1 over x. So you want to calculate f of 1 over x. So you have f of x to be x squared minus 1. Okay. And you want to calculate f of 1 over x. You take out the x and you replace by 1 over x. That's what you got. All right. And if you want to simplify further, you can just write this as 1 over x squared minus 1. So you get this is 1 over x squared minus 1. Or that 1 over x squared minus 1. All right, so most of you did well on B, a little bit of problem with C, problem with D, okay? So let's work together on this. So for B, G, circle with f of x, this give you G of f of x. Given that f of x is equal to x squared, so you have G of x squared minus 1. All right, so you get 1 over x squared minus 1. All right, so part B, you should get something like this. Now for f circle with itself, you have f of x. Now f of x is equal to x squared minus 1. Okay, so bear with me here. So again, f of x is equal to x squared minus 1. Now you're looking for x squared, f of x squared minus 1. So you take out the x and you replace that by x squared minus 1. Most of you get up to here. Okay, good. All right. Now, if you want to manipulate the results, most of you, unfortunately, give me x to the 4 plus 1, which is not correct. All right. So what do? Here you do x squared minus 1 times x squared minus 1. Then you expand it that way. Okay. So you distribute your FOIL. And then you have x4 minus x squared plus 1. then -1. Cool. Therefore, you get x to the fourth minus 2x squared. So this one and -1 cancel out. Kabish? Good. So now f of x squared minus 1 should give you x squared minus 1 altogether square minus 1. Okay. And x squared minus 1 altogether square should give you x to the fourth minus 2x squared plus 1 minus 1. Or this is x to the fourth minus 2x squared. Now G circle with G of x or G of x. G of x is 1 over x. So most of you get this. Most of you give me 1 over x. All right. So now in this case, you define a fractions. That means you can multiply by the reciprocal. Just give me 1 times x over 1 or just x for the answer. Cool. Good. Questions? All right. So we have done some algebraic approach for combining two finding composite functions. Now, in example 5 and example 6, what we do is that we're going to do some combined function, finding some composite function, and then evaluate the function at certain points. So in example 5, you're given two graphs, f of x and g of x with some values. For part A, you have f plus g of 3. That is f of 3 plus g of 3. And then from here, you look at the graphs and give me the values. So f of 3 is equal to 2. Yes, x equal to 3, f of 3 equal to 2. And g of 3 is equal to 1. Then add the two values together to get the answer. So f of 3 is 2 plus g of 3 is 1. Give me 3. Easy, yes? Now f minus g of 1. Give me f of 1 minus g of 1. So f of 1 is 2 and g of 1 is 3. So 2 minus 3 is -1. F times g of 4 is f of 4 times g of 4. Given that f of 4 is equal to 4 and g of 4 is equal to 0, the answer is 0. Now d is the quotient functions. F of g of f over g of 1 is f of 1 over g of 1. Given that f of 1 is equal to 2 and g of 1 is equal to 3. So on the left-hand column, we just finished some combined functions. On the right-hand column, some composite functions. So f circle with g of 2. Give me f of g of 2. What is g of 2 equal to? 2. So you technically calculating f of 2. And f of 2 is equal to 0. So f composes with g, evaluate at 2 will give you 0. Questions? Now f circle with g of 1 or f of g of 1. So g of 1 is 3. So f of 3 is equal to 2. G of f of 2, that is g of f of 2, given that f of 2 is equal to 0. So g of 0 is, what is g of 0? 4. Now g composes with f of 3, so g of f of 3. So f of 3 is equal to 2, and g of 2 is equal to 2 as well. Questions? Yes. Okay. This 2 or this 2?
Either.
Okay. So f of 3, so that means that we go to the graph of f. So this is the graph of x. So x equal to 3, so f of 3 is equal to 2. So that's the first two. Now we calculate g of 2. So g of 2, you go to g 2. That's good. Yep. No problem. Good. Any questions? Now let's move on to example 6. Now instead of graphs, you have the table of values. And we're gonna do a similar exercise. Okay. Can you spend a little bit of hold on. We have 4 more minutes. Yes. Okay. So let me do it. So you have a table of values. The first column row is for x. The second row is for f of x, and the third row is for g of x. Now you do f plus g of 1. So give me f of 1 plus g of 1. So f of 1 is 2 plus g of 1 is 3. So this is equal to 5. Let me stop me if you have any questions. Okay. I rather teach you 17 lesson, but you understand the 17 lesson, than give you like 30 lesson and you don't understand how. Okay, so let me know if you have any questions. Don't hesitate. So f minus g of 2, that is f of 2 minus g of 2, given that f of 2 is equal to 3, and g of 2, so right here g of 2 is 5. So 3 minus 5 is negative 2. F times g of 3, that is f of 3 times g of 3. Given that f of 3 is 5 and g of 3 is 6. Get 5 times 6 give you 30. Then the last one is f over g of 4. Give you f of 4 over g of 4. F of 4 is 1, g of 4 is 2. So you get 1/2 for the answer. Good. Now for e composite functions, f circle with g of 6, give you f of g of 6. And g of 6 is equal to 4. So you're calculating f of 4. So f of 4 is equal to 1. Good. And f circle with g of 5. F of g of 5. G of 5 is equal to 1. So f of 1 is equal to 2.
So hopefully at this point, you're comfortable with these calculations, okay? You know where the answer coming from, okay? So I'm gonna split up on the last two examples, last two parts. G of f of 4. F of 4 is 1. G of 1 is 3. And G composes with f of 3. So G of f of 3. F of 3 is 5. And G of 5 is equal to 1.